Yes, and now let
Did it work?
me introduce you. So today we're very pleased to have Courtney Paquette deliver the Tutte Colloquiua. Courtney completed her PhD in mathematics at the University of Washington in 2017, followed by postdocs at Lehigh University, and most recently in CNO, before going to her current position at Google Brain in Montreal. And she will be joining McGill as an assistant professor in the coming months. Courtney's research is in optimization with applications in data science and AI. And today she'll tell us about halting time is predictable for large models. Courtney.
Thank you, everyone. So before I start really into the talk, I want to say that this is actually this is a work in progress talk. So please ask questions. This is the first time I'm giving this talk. I'm interested in hearing sort of what other people's opinions are on this and sort of where I can go with this, especially if you are interested in it. So this is a joint work with my collaborators at Google Brain. So it's with Bart and Fabian and my husband, Elliot, who had a lot of help with the random matrix theory aspects of it. And so today I want to focus on average case complexity of optimization algorithms. So the idea here is that we're trying to minimize some function f of x, and we're going to run some optimization algorithm off of it. And the question is sort of what is the average case complexity of an optimization algorithm? And here we define average case as the complexity of an algorithm averaged over all possible inputs. Now, from computer science and numerical analysis, this idea of average case complexity has sort of been, at least understood in some. The condition really have this idea of what it means to be an average case for an optimization algorithm. When you hear people talk complexity results in continuous optimization, they're almost always stated, which are great because worst case guarantees convergence results, but they may not be representative of the typical behavior of an algorithm. And you might say, so what are some of these difficulties? Why can't we use average case analysis for optimization? Like, what are some of the problems with it since they're so good in other areas? And I think there are maybe three, probably even more, things which affect average case complexity. The first is that because you're talking about an optimization and problem, average case starts off with just sort of what is a typical function that you have to be minimizing over. And there's no clear answer, like what do you mean by a typical convex problem or a typical strongly convex problem? Very clear what that means. The other thing I think, which is maybe sort of people believe, is that there's this real sensitivity to sort of the function itself, that the optimization algorithm is highly dependent upon sort of the inputs that you put into it. So there's a sensitivity to this input. And the third thing, which turns out to be harder than you expect, especially if you've ever done complexity analysis before, is that in order to do average case, you have to have exact expressions. Like as soon as you do a bound, you're in trouble. And this is actually a problem because when someone gives you a convex function, the first thing you do is you bound, right? So as soon as you bound, you're out. And this is actually a little bit hard to do for average case. That being said, average cases, like I said, a huge history in numerical analysis and in computer science. We know things like quicksort, algorithms, and probably the closest thing in optimization that we have using average case is the simplex method. And they did this via smooth analysis. And I just want to start off by saying I'm not doing smooth analysis. Okay, so I'm not going to be talking about the smooth analysis framework. The other prior work I wanted to emphasize here is that about 10 years ago, people started noticing linear algebra algorithms, so things like QR factorization, Jacobi iteration, that the algorithms were somehow insensitive to the inputs. This was observed by people at NYU, And I think even up till now, it still hasn't been solved why that's true, but the empirical evidence is out there that these numerical algorithms are much less sensitive to the inputs. And this actually was the inspiration for this talk and for this result that we had, because we saw this in these linear algebra, and we thought maybe it holds true for optimization algorithms too, kind of by luck. I see that. So again, the goal of this is that we're trying to understand sort of the average case complexity of an optimization algorithm. And so we have these three sort of difficulties. And so the first one I think we have to tackle is that you have to say, what do you mean by a typical convex or strongly convex problem? And so the way we handled it was we thought, okay, what's the easiest non-linear optimization problem that we can think of? And I could probably take a poll, but maybe some of you might guess. I would think that the easiest one to try to start off with is least squares. People agree with me or not, but I think it would be least squares. So we decided to try that. So we went and said, let's look at the simplest one we can think of, random least squares. And when you start to think about random least squares now, you can understand that it's a lot easier to understand what you mean by inputs. Like what are you going to make random? What are the inputs into this problem? For instance, the inputs into a random least squares problem is going to be the data matrix A and the sort of outputs B. So here we're going to assume that we take a random matrix A and a random vector B, and we're going to form the least squares problem from it. And so we just said, okay, well, let's just run some algorithm and let's figure out the number of iterations until the gradient is less than epsilon. We call that the halting time. And shockingly, maybe it's not shockingly for everyone, we saw this really cool phenomenon happen. So here we ran gradient descent on the least square problem, and what we saw is here on the x-axis is the dimension of the matrix. Okay? So this is your model size D, and then we ran gradient descent. We generated these random A's and B's. We ran gradient descent on them, and we computed the halting time for each dimension. And we did 8,000 gradient descent. We, in some ways, broke Google servers. They got angry at us because, you know, you're using up all their power just to generate least squares problems, which is probably not the best use, but it was really cool, the results that we saw. And so we did this, and this is exactly what we saw, is that the shaded areas here are the standard deviations of the halting time dimension. And what you see is that as the dimension grows, so as this matrix gets bigger and bigger and bigger, the halting times, number of iterations until the gradient is less than epsilon, actually converges to some constant, that the variance is going down to 0. Moreover, we did this where we generated A using two different sort of models. We generated one using a Gaussian data, and we generated one using a Bernoulli data. And again, what we were surprised with is that even though these two things were generated, these random matrices were generated using different distributions, they all converged to exactly the same value. We saw this universality property happening, that the distribution, the halting time was independent sort of the distribution of the. And when we were shocked, we were like, okay, this is something very interesting, sort of unsurprising. I hope other people think it's surprising. And so we're like, maybe this is just a factor of gradient descent. Like maybe this gradient descent does this. It turns out that basically all first order algorithms have this sort of property, that the halting time becomes sort of predictable as the dimension starts to grow, and it's like insensitive to the input distributions. So we were shocked. So first of all, I'm going to pause. Is there any questions on this? Does this make sense? What's going on? And it's like insensitive to input distribution going on. Okay, I assume that's no. So then this led to, so the idea here now is maybe what's going on, a model that we use.
Courtney, there is a question in the chat.
Yeah.
From Henry. Yeah. Henry asks, is this because of expected condition number?
Part of it is, but it's not. So you're right. It's related to condition number. But in fact, what you'll see is that the algorithm actually needs to know all of the eigenvalues of the matrix A. But there's properties. But it is, yeah, the idea behind it is related to conditioning. Yeah. Good. People. Okay. So again, here I want to talk a little bit more about how we actually generate these random matrices and random vectors. So the approach that we took here was a generative model. So the idea here is that we're going to generate a random signal, x tilde, and a random noise vector. And we're going to form our B by taking A times that signal plus the noise. And we're also going to do a random initialization x sub 0. And how did we choose this x tilde and noise? Well, we chose it so that the signal to noise ratio is constant. So what this means is that sort of as you grow in dimension, neither the signal nor the noise is dominating each other. They have the same sort of impact at all dimensions. It's important to get the scaling. So that's why you'll see some weird scaling happening here. But the goal was that we wanted to maintain that as the dimension increases, the signal and the noise have the same strength. Okay. That's the idea. And then, of course, the big question is how do you actually determine the matrix A? And so the first model that we looked at, the first ensemble that we considered was sort of this very classical random matrix theory. And this idea was to use that the entries of A are IID independent, and that each one has sort of a constant variance and bounded force moments. And you can kind of think of this as the same requirements as central limit theorems or law of large numbers. That's very cool. Now, because this is not as realistic to machine learning, we decided we had to do at least something with machine learning. So we also did a different model, which is that we looked at a one hidden layer neural network. So the idea here is that you're going to generate two random matrices, and you're going to multiply them together, and then you're going to take an activation function pointwise on those entries of those two random matrices. Okay. And so the least squares problem, it's still a least squares problem, but it has this sort of funny G composed times x minus b, and you're still just minimizing over x. Okay. And the idea here is that why it's related to neural networks is that you can think of this as a two-layer neural network, where the first layer, the weights, are random, and the second layer is just given by your coefficient x. And where this thing came up, why this is used so often, is that it was first proposed by Ben Recht for scaling up kernel methods. And then the neural network people took over machine learning and realized that this sort of model here has actually really good generalization properties. So these generalization properties mimic the neural networks that you really see. And so that's why people use this as a model for neural networks, that they have the same type of generalization property as neural networks do. Any questions on the data distribution matrices? All right, so now I have to go into a little detour into random matrix theory. So it turns out that the most important thing in this talk is not going to be the matrix A, but actually going to be the matrix H, which is just A transpose A, and which is the sample covariance matrix, I think, in statistics. And it turns out, thankfully, that random matrix people have studied this matrix to death. They know all sorts of properties about it, and so it's really cool. So under those assumptions, under those two data distributions I just showed, what random matrix people assume is that they first assume that the ratio of the model size to the number of samples is constant. So this is a little bit weird for machine learning and optimization, but what this means is sort of that as you add another feature, you also add another sample. That's the correct scaling that you need when you want to compare across dimensions of matrices. It turns out this is just a random matrix theory fact. The second thing that random matrix theory people have studied is that they really studied the properties of the eigenvalues of this matrix H, which goes back to Henry's question. And so random matrix theory people know and have proven that the empirical distribution, the empirical eigenvalue distribution of this matrix H actually converges to a known distribution. So what this means is that if you were to draw an eigenvalue from this matrix H, it has a certain distribution which is known to random matrix theory people. Okay? Now, they don't actually have an explicit formula for this mu, but we know it exists. Maybe the third and fourth, I guess, thing that I assume here is that I need something about the largest and smallest eigenvalue. And this is important simply because the algorithms themselves often use largest and smallest eigenvalues as part of, just their iterations. So I'm going to assume here that the largest eigenvalue and the smallest eigenvalue of H converge in probability to the largest value of mu or the smallest value of mu. And again, the goal of random matrix theory is to prove all these sort of matrix ensemble type things, like what I just saw, those data matrices, that they actually just have all these properties that I just wrote down. So what we know from Bai and Silverstein is that the isotropic features satisfy these four assumptions, and from Pesce, the one hidden layer neural networks also satisfy these four assumptions. And I mentioned that the most important thing here is that the empirical eigenvalue distribution of H is converging to some known measure. Now, the problem is that you don't actually have an explicit formula for it. However, we do know what it is in terms of when you have these isotropic features. So the ones where you just have IID entries. Okay, so the simplest model. And in this case, the empirical distribution of the eigenvalues of H converge to something called the Marchenko-Pastur distribution. And so I drew the Marchenko-Pastur distribution. By the way, I hope someone is in the audience who knows random matrix theory. There's a lot of random matrix theory, and there's a lot of interesting questions related to it, which I'm not an expert in, but I think would be cool to study more. So this Marchenko-Pastur distribution has this interesting property. So basically it's dictated by this value R. So when R is not equal to 1, okay, that means that D is not equal to N. That means you're not in a square matrix kind of setting. There's a gap between the non-zero eigenvalue, the first non-zero eigenvalue, and 0. Okay, so there's this nice gap that occurs. As R gets closer and closer to 1, this gap between 0 and the first non-zero eigenvalue disappears. Okay, so what this means is that when you have square matrices, your H becomes more and more ill-conditioned. Okay? But you do have eigenvalues which are extremely small, that are extremely close to 0. Any questions on this? No? Okay. Cool. All right, so let's go back to this question that we really were trying to show, which we saw from empirical data, which is that, all instances of high dimensional data kind of look the same to first order algorithms. So you might be saying, how are we going to show this result? This seems like a very, very broad result. So we go all the way back to, I would say, the 1950s, maybe sooner, maybe earlier. Somebody else may have some more information on this. And the idea is that because we're working with least squares problems, that every first order method is actually related to a polynomial in H. Okay? So we can think of first order methods as just polynomials in H. And I think this idea comes from CG methods. Tell me if I'm wrong from someone in the audience out there. If they think. So just to give you a little bit of an example of this, let's look at gradient descent. So gradient descent, we're just going to move in the direction of negative the gradient. So ignore the x tilde, but you get xk is equal to xk minus 1 minus some constant times the gradient of f. And if you plug in what the gradient of f is, you get something which says that xk minus x tilde is equal to identity minus h times xk minus 1 minus x tilde, plus a little noise because of I added this noise to b. And then you do this iteration again, and so you get identity minus h times identity minus h minus x minus k minus x tilde plus noise, and you keep going all the way down, and so what you end up showing is that xk minus x tilde, the signal, is equal to some polynomial, which looks like identity minus h, some power, plus some noise. And this plus noise actually also turns out to be a polynomial in H. So you see that gradient descent has a very explicit polynomial in H appearing. And I think CG has a very explicit polynomial in H as well, involving Chebyshev polynomials. But it turns out every first order method has it. So I graphed what Nesterov accelerated polynomials look like. They're not explicit. The reason why they're not explicit is that they satisfy some sort of recurrence relationship. And so I don't know exactly how to get an explicit form for them. But the recurrence relationship is all that we need. So, sorry, someone sending me a message. The next question is, so how do you actually start to analyze the typical behavior of an algorithm? So I think there are many ways you can start to think about this as. One of the ways is that you can think of this as sort of like analyzing the gradient of the algorithm after k iterations, or the function value after k iterations, or the iterate after k iterations. So today I'm going to take the gradient approach. You can do all of this for function values. You can do all of this for iterates as well. So what it turns out, because of this cool relationship between polynomials and first order methods and the iterates, the gradient of the function after k iterations is actually basically equal to the trace of the polynomial in H. So this just says that the gradient of the function is basically determined by the eigenvalues of H, which is pretty amazing. And so this is why random matrix theory starts to come in, because you can say, oh wait, I took this random H, and random matrix theory tells me, you know, as I look at the empirical distribution of the eigenvalues of H, I actually know what they become. I actually know all the information about these eigenvalues. They go to some deterministic distribution that I can work with. And so with that, because we can use that, we can actually say basically anything we want about the algorithm. Okay? So what we showed is that the gradient of f actually concentrates, and it concentrates to this really cool value. It's an implicit. And so what you see here is you see the effect of the algorithm, the data model, your signal, and your noise all have on the gradient of f, like exactly how they are related. This is not like inequality, these are equalities all the way. So we see, you know, the signal is hitting this sort of integration. The optimization algorithm is entering through by sort of the polynomial, which is what we're integrating against. The model that we're using comes through in sort of the distribution of the eigenvalues that we have. And then you'll see this R again, number appearing. So you get to see explicitly what the gradient is converging to and how each component of your input affects the resulting gradient of your algorithm. I think this is really cool. I can pause for a moment if there's any questions on this or if this makes sense. Everyone okay with this? Okay, I'll go on. So once you know what this, this gradient is converging to, that it's concentrating around as the dimension grows, you can actually then talk about the halting time. And so what this right-hand side I'm going to call is sort of the average case. It actually is exactly the average case. So it's this expectation, sort of what happens in the limit. And what you can show is that the number of iterations till the gradient is less than epsilon is actually equal to this average case value, this expectation value. And we showed this. This is the halting time result. Okay. And so this is all going back, this proves sort of this idea that we saw at the very beginning, that these different data ensembles all have the same limiting distribution and their variance is going down to 0. So in high dimensions, the halting time is just predictable and it's insensitive to the data that you started with, which I think is really cool. And so I also wanted to show you, because you see, like, you might ask, well, what happened when you're in low dimensions versus high dimensions? And in the low dimensions, what we saw was that the distribution of the halting time was kind of skewed. There's a tendency for it to be a lot lower than the mean. So you kind of can see this, it has huge variance. It was much, much more variable. Whereas once you got into the high dimensions, basically everything was like the same value. It got really bad because you generate like 8,000 least squares problems for like a huge dimension and they're all exactly the same. Yeah, we were wondering how we could get away with this from Google, but it's pretty fun. The other thing to note is that empirically, it looks like the standard deviation is decreasing like d to the 1/2. So this is kind of a common thing that you see in random matrix theory, that the standard deviation decreases like this factor. So agree. And then we're like, okay, maybe, maybe it's least squares, maybe we should try some other things just to see what happens. And it turns out things like logistic regression also have this property. We don't know how to prove it because you don't have this polynomial, but logistic regression has the exact same sort of look as least squares does. And we also thought, okay, it worked for first order methods which were deterministic. Does it also hold for methods which are stochastic, sort of like SGD, stochastic gradient descent? And so we tried it on stochastic gradient descent and it also had the same behavior. Which we thought was really interesting as well. And so we really want to try and explore these stochastic methods also. Is there any questions on this?
Yeah, I had a question.
Yeah.
So I've heard some analyses of first order methods as like approximating a continuous process.
Yeah.
And it seems like all of these stochastic versions are also approximating that same continuous process. Do you have a way to analyze the continuous process?
Yeah, so that's a good question. In the stochastic ones, it seems like the process that it converges to is actually like a solution to a PDE problem. And so it's not as straightforward to analyze. The first order methods, like you said, are much simpler to analyze what they converge to. We know more about them. The SGD ones are like PDE solutions due to their stochasticity. And we've been working on the SGD version of this, but we haven't fully proven the concentration result for it. Yeah, any other questions? Cool.
Yeah, I had a question.
Yeah.
So I just missed it maybe, but are your first order methods using an exact line search, or is it something like a wolf?
No, so I'm not doing with line search. That's a good question, except for maybe CG also will work on this. I'm just like for gradient descent here, I'm just assuming that I'm using 1 over the Lipschitz. So the Lipschitz constant for least squares is the maximal eigenvalue of A transpose A. So I'm not doing anything fancy with line searches. It's a good question to see, does this property actually hold for line searches? I know it works for CG. So my guess is it probably does work if you replace the step size with something which is adaptive. But it is a good question to ask. It makes the analysis harder, but it is doable. Yeah, I'm taking the simplest approach. We just needed to prove concentration first, so yeah. Any other questions? Cool. All right. Hopefully that made sense. So this now that we sort of had this concentration and we sort of know sort of implicitly what the average case complexity of an algorithm is going to be that integral thing. Can we actually get more of an explicit form for it? And so with isotropic features, because we know that measure that it converges to, we have an explicit formula for what it is. We can actually start to analyze it. So in this section, I'm just going to be working with isotropic features and gradient descent. I'm still doing some work in progress, like I said, with other first order methods. And like I said, if people are interested, I would love to see if we can expand this idea more. So as I mentioned, with the isotropic features, we actually know the distribution of the eigenvalues. Like we know everything about it. And as I was mentioning, because it converges to this Marchenko-Pastur, that we know its relationship to R, to the value of the ratio between the model size over the number of samples. And the idea again is that when R is not equal to 1, so you're not in the square case, the gap between the first non-zero eigenvalue and 0, there's an actual gap, a legitimate gap. But as R gets closer to 1, as you become more square, this gap disappears, and you have eigenvalues which are really, really small, and you have a chance of hitting those eigenvalues which are really, really small. And because convergence algorithms, optimization algorithms depend on the sort of the eigenvalues. We expect different convergence behaviors when R is equal to 1 and when R is not equal to 1. So when R is not equal to 1, we really do have something which is behaving more like a strongly convex objective function. And when R is equal to 1, we have something with eigenvalues which are really, really close to 0. So it's not strongly convex. It's behaving more like a convex function. Okay, so we do expect this sort of dichotomy when you see R equal 1 and R not equal 1. And it turns out with gradient descent, by what my husband said was a miracle, that you can actually just straight up integrate against this measure. You can just write down the formula. So we wrote down the explicit formula for gradient descent with this measure. So the gradient of f actually converges to a term which involves the signal and the noise, okay, as you can imagine. And when R is equal to 1, the gradient converges to something which with the signal looks like 1 over k to the 5 halves, and with the noise looks like 1 over k to the 3 halves. Okay? And when R is not equal to 1, you get this beautiful linear rate, just like you expect. And the linear rate is governed by the smallest eigenvalue over the largest eigenvalue, so the condition number. So when R is not equal to 1, it's kind of like the only things which matter are the largest and smallest eigenvalues. So this kind of goes back to Henry's question about the condition number. When R is equal to 1, there's much more going on with the eigenvalues. Like all the eigenvalues are starting to contribute a lot more. Okay. And so just to sort of illustrate, how this this ratio R is actually appearing in everything. We ran this, and so what you can see here is that we varied R, okay, and we varied the noise level. Okay? And when R is close to 1, you see a huge spike in the number of iterations to reach the nearly optimum solution. Okay? And this again agrees. And as the noise level increased, the spike got bigger and bigger and bigger, just as you might expect, because that second term with the noise is contributing more and more and more. Okay? In SGD, it was even worse. When R is equal to 1, it took forever. I think there was one point where we were running it where the server told us it would take 3 months to solve. So we decided that was too long. But it takes a very long time in SGD when R is equal to 1. Okay? So you really do see this behavior. So just to give you sort of a comparison to worst case rate, what we saw was that, you know, when you have an R not equal to 1, when you're in the strongly convex setting, that the worst and the average are pretty close. You get a linear rate, and the rate is determined by basically the largest eigenvalue over the smallest eigenvalue. So there's not too much difference between average and worst in that setting. You still are better, but not by that much. When R is equal to 1, that means you moved into this case where you have very, very eigenvalues which are really, really close to 0. This is when you start to see differences appear between average and worst. So when you have no noise, it's really apparent that the average is just much, much better. You gain a whole factor. So instead of being 1 over k squared, it actually takes 1 over k to the 5 halves, which is a significant improvement in the average. Now, what's really crazy is then we went to this setting where R is equal to 1, but we added noise. And something weird happened. It looks like it might be worse in the average than the worst case. And we were like, huh, what's going on? That's really bad that the average is worse than the worst case. Something's going totally wrong in that setting. So we wanted to explore this a little bit more. We wanted to see what happens when R is equal to 1, so you're convex, so you have eigenvalues really, really close to 0, and you have noise. Okay? So you added this noise to your optimum. And so the worst case, what we saw, and maybe some of you know this, but the worst case is basically dictated by the eigenvalues plus the distance to the optimum. And what we discovered was, or maybe we didn't discover this, but we realized what was happening was that there's really a big distinction to be made about the signal. You know, I generated my data, my B, using the signal, and the actual optimum that you get from running the algorithm, like the thing that the algorithm converges to. And it turns out that if you want to make your signal to noise model constant, so if you want that as you grow in dimension of your matrix, the signal does not dominate the noise, that they always stay the same sort of value as you grow, that it actually causes the distance to the optimum to grow in dimension. And this is basically because the noise starts to become sort of a feature. It affects everything. This noise. And so what we showed is that the distance to the optimum is actually kind of growing in dimension. And this actually sort of explains why the worst case rate, when you first look at it, is better than the average. It's because the distance to the optimum is actually growing in dimension. And so the idea, so what's going on here is that, you know, the average case is kind of better in some ways when your iterates are much, much smaller than your dimension. So when you are running your algorithm before you hit the end, so when k is less than d, that's what's happening. The other thing to make note is that we were like, okay, well, maybe we should normalize by the distance to the optimum. I mean, that seems like the most natural choice here is can we normalize by the distance to the optimum? But I don't actually know how to do that. And maybe people in the audience here can answer this question is, how do you actually normalize by the distance to the optimum and generate your data in such a way? It's not clear to me. The only way I know how to do this is to lose the constant signal to noise and basically make the signal become more dominant as the dimension increases, which I don't think is realistic. So if people have some insight onto that, I would love to hear what people have. And so then we were like, okay, let's just make sure that average is better than worst.
Hi, Courtney. Sorry to interrupt.
So we ran this again in the non-strongly convex with noise. And what we saw was that the empirical runs exactly matched the theoretical rates. Like they were exact, okay? It doesn't even look like this, so this is in the top graph here, that we ran this like 8,000 times, but we did. We ran least squares 8,000 times and recorded what the convergence rate looked like, because they're all identical. Like there's no variance in these.
Courtney, there's a question from the chat.
Yeah.
Henry asks, why is worst case independent of any scaling? Divide by objective value when stopping?
Yeah, so sorry, maybe Henry can elaborate more on that?
Yeah, well, usually stopping criteria doesn't just use the gradient. It uses the gradient divided by value of the objective plus 1 to avoid 0.
Yes,
so if your functions are totally different in magnitude, that seems to be ignored here.
So you have to be a little careful. Let me go back a little bit. We've divided our function values by dimension. So there's a scaling already as part of the function values. Does this make sense? There's all sorts of things about scaling in here just to make the function values kind of on the same level as dimension increases.
So that was for the least squares, but for the problems that were not strongly convex, do you have any scaling there?
They're all like that. So we're only dealing with least squares problems.
Oh, okay.
Yeah, so what I mean by, and this is a good question, what I mean by in the non-strongly convex case, is you're right, if you generate a random matrix at any dimension, the chances that it has zero eigenvalues which are 0 is basically 0. Like it will always have non-zero eigenvalues, okay? But the idea is that as you grow in dimension, there's more and more chance that those eigenvalues become closer and closer to 0, if that makes sense. So the eigenvalues get smaller, have a higher chance of getting closer to 0 as the dimension of the matrix grows. And that's what I mean by it's sort of resembling a non-convex problem. It's sort of resembling a convex problem, not strongly convex. Does that make sense, Henry?
Yeah,
your question?
So are you in some sense got a similar objective value for all your problems?
Yeah, the objective value is the same. It's just that you're varying dimension. So you're making dimension get bigger and bigger and bigger. And when you do the dimension getting bigger and bigger and bigger, what happens is that the eigenvalues actually get closer to 0 if you have a square matrix. So if A is square. Turns out.
Hey, thanks.
Yeah, okay, cool. Sorry, I forget where I was. I think I was here. Yeah, so I wanted just again to say that what ended up happening is that we wanted to make sure that these rates actually match what you saw. And because everything is equal here, once your dimension gets large enough, the variance goes away, and actually these theoretical rates are exactly what you see. And they're not just exactly what you see because of an averaging effect, they're exactly what you see if you just run a single least squares problem in high dimensions. They're the exact rates. It was absolutely amazing. And then we wanted to, again, showcase why worst case, this sort of weird distance to optimum that we were having problem. If you actually plot sort of the worst case divided by sort of the average, because x0 minus x star, you're generating a whole bunch, so x star is changing, and you have noise, you get this crazy orange curve of distribution. So average was always better because the thing is always bigger than 1, but you see that it's highly, the worst case is very sort of unstable. The x0 minus x star, that distance to optimum, is like unpredictable. And this is simply just because of the way we did the constant signal to noise. So again, just to sort of summarize, in fact, although it doesn't look like it, the average case is actually always better than the worst case. And particularly this is true when the dimension of your matrix is much, much bigger than your iteration count, which is what you would expect to have in large models. In large, when the dimension of your matrix A, when you have lots of samples, when you have lots of features, the average case is better. So it's better, and we have rates for all of that. And so I just wanted to end here by saying that we had this nice, cool general framework that we saw from doing the concentration of the gradient and how it related to sort of universality of first order methods. And then in some cases, we were actually able to get average case analysis. And sort of our work in progress is to sort of extend these ideas of universality, the sensitivity to the inputs, to other algorithms like SGD, other functions, do the average case for first order method. I think we're getting close on that. But there's a lot of other open problems, and I'm hoping people might be interested in them, which is that what happens if we do different matrix ensembles? Like for instance, these ensembles, how I generated my matrix A, sort of imply that the matrix is dense. So what happens if you assume sort of a sparse structure on it? What goes on? Do we see universality results? Do we not? What are these extensions to things like non-convex functions? It's clearly there's some connection with, at least the way I presented it, with eigenvalues of this matrix. So, you know, PCA, matrix completion, these are all related to eigenvalues. So maybe we could say something similar. And then the question is, how does this relate to things like subgradient methods? Like if we place the 2 norm with a 1 norm, will it still work? What do we see? I think those are really interesting problems. If people are interested, if you're interested in random matrix series, I have tons of random matrix series questions involved. But yeah, I would love to hear people's opinions. So thank you, and I managed to get it onto arXiv, this paper. So this is the arXiv paper that this talk was based upon. So thank you guys very much, and I'll end here. Thank you.
Thank you, Courtney. So at this point, we have time for some further questions. So I'll open it up to the audience. Please unmute yourself and feel free to just interject with a question. Courtney.
Hey, this is Steve. Hi, Courtney. Can you hear me?
Hey. Yeah, I can.
What's wrong with my camera? Sorry. So I tried to turn the video a few times and it kept saying you can't detect my video. So anyway, yeah. So nice talk. And one question that springs to mind because of the work that you did at Waterloo, which is that maybe in the ill-conditioned case where there's noise, you're sort of driving the residual down to epsilon for an arbitrary epsilon is too much, right? Maybe for the application problem, you didn't need that. Would that change your results or the kind of thing you'd be looking for?
So you're thinking of a different stopping time? Is that what you're?
Well, in other words, if the problem is ill-conditioned and the data is noisy, then it doesn't necessarily make sense to drive the gradient down to an arbitrarily small epsilon, right? because you've already somehow solved the problem before it gets that small, right? You see what I'm saying?
Yeah. I think that relates, so the way you would do it is that you would want to relate that to a different sort of stopping criteria, and then something which it's different relationships. So as long as you can prove sort of this concentration, so like I showed that the gradient of the function converged to some value. It concentrated around this value. This holds for function values, this holds for iterates as well. And if your stopping criteria that you want to stop sort of before it's in relationship to one of these three values, I think it will still hold. The universality type property will hold. That you don't need to drive, like you don't need to look at just the gradient being less than epsilon. We did that just because it was the simplest and the one which we could actually compute things with and was the most well known, but I think it will work. But like, I think there's a lot of room. Like, I think there's a lot of interesting areas we can go with this.
Okay, all right, that's all, thank you.
Okay, we have time for another question. If
I
there's
have a couple. Nobody else is asking. I already asked a couple. Can I ask? It's Henry.
Yeah. Hey.
Okay. So a couple of questions. One is, so these conjugate gradient first order methods are very much connected to Krylov methods for the least squares problem. And the Krylov methods depend on the number of distinct groups of distinct eigenvalues you have, rather than just the largest and the smallest. So that was my first question. And the second question is, can you say anything about moving to quasi-Newton from the first order?
Okay, so your first question, like CG conjugate gradient, it has the same properties as all this holds for CG, basically. And I think the way to see it is not through Krylov methods, like thinking of it as a Krylov subspace, but to think of it as, if you think about how they prove CG, they go through Chebyshev polynomials. And so this is actually very much related to Chebyshev polynomial. And in fact, a lot of the first order methods, not just CG, Nesterov, Polyak momentum, all go through Chebyshev polynomials. They're just scaled versions of the same polynomial. So that's why those things see the same rates, and you get the same result. For quasi-Newton, I think that's actually a place where we could try and do things. I don't know. I don't know what happens with quasi-Newton. The polynomial, I think, becomes a lot harder. It's not necessarily a polynomial anymore. And so I think, like I said, I think that would be a really cool area to see. Do we see these universality results? Can we actually get average case results for quasi-Newton? I don't know, but I think this framework might work. So yeah, I'd be happy if you want to talk more about that offline.
okay. Last chance for questions. If not,
I'm just curious about. I just have a question. I'm curious about like the distribution of eigenvalues for randomly symmetric matrices. So does it matter like how the random symmetric matrices are generated? Like, do they always follow that distribution?
That's a good question. So I'm not a random matrix person, but the ones, if you generate it using so isotropic. So if you have mean zero, variance of each of the entries is the same, and the fourth moments are bounded, the distribution for the eigenvalues is the same. So the distribution for the eigenvalues and the limit always converges to the Marchenko-Pastur. For things like this one hidden layer neural network, we know that they converge to some distribution of the eigenvalues. We just don't know. We don't have like an explicit formula. We don't know what this distribution looks like. Does that make sense? We know they converge to the same distribution. We just don't know what that distribution is, like what it looks like explicitly. But from random matrix theory point of view, they've also studied other ensembles of random matrices, meaning they've studied other different characteristics than these like mean zero IID things and proven sort of the same type of results. And maybe if someone is a random matrix theory person in the audience, there's a lot of questions and observations that use random matrix theory that I would love to pick their brains on.
Okay.
Hopefully,
Thank you.
Great. So at this point, let's thank Courtney again for a fantastic talk. And at this point, I'll stop the recording and ask Courtney to